let's talk about bonding. Now, this is just a little bit of physics involved here. We're going to start out with this, a proton and an electron. And you know what? We got to talk about why does the electron go in the orbit? What is that called? The Bohr model? Sound familiar? Yeah. Isn't there a velocity here?
Yep.
Sound good? Why does the electron stay in this Bohr model orbit? Yeah, what's pulling it inward? Is it gravity? How about an electrostatic force? Isn't that what holds it all together? So, does the electrostatic force produce the centripetal force? Sound familiar? Didn't we talk about this with the Earth going around the sun? In that case, it was gravity. Does gravity hold the atoms together? No. Gravity, some people are going, yes. No, gravity doesn't. Gravity is a very weak force. You need something much stronger to hold the atoms together. The electrostatic force, give me the formula. Give me the formula for FC. M, thank you, V squared over R. So if I knew the radius of, say, a hydrogen atom, and I knew the charges of the electron and the proton, and I knew the mass of the electron, what could I solve for? Yeah, you can calculate how fast the electron goes. If you want to read about this, it's in the packet. I'm not going to emphasize that. It's just, I think, pretty cool to see how high school kids can calculate stuff going on in the atom. Is this macroscopic or microscopic? Microscopic. And we've been talking about macroscopic stuff, haven't we? Well, we're going to go between the two. Let's talk about this now. What if you had a hydrogen atom and another hydrogen atom? This is H bonded to H. That's an H2 molecule. Does that sound like anything you've heard about before?
Yeah.
So what holds these things together?
Intermolecular forces.
Okay, in this case it'd be interatomic forces, I guess, but it's all along the same lines. Does the proton do something to that proton?
Yeah.
What?
Pushes.
Yeah, that's a repulsive force. What about this? Also repulsive. What about this? Attractive forces, and the same way here. Does everybody see that? Somehow these forces should work together to form a bond. So a long time ago, I played around with some math on this. I said, I wonder what that repulsive force is. I wonder what that attractive force is. But could I just calculate it at one position?
No.
The electron keeps moving, doesn't it? So I calculate it for here, I calculate it for here, I calculate it for here, and I go all the way around. And guess what I come up with for the sum of the attractive and repulsive forces?
0.
Yep, 0. I thought that doesn't make any sense. But then I thought, where's the average position of that electron?
Everywhere.
Not everywhere. Average. Sometimes it's up, sometimes it's down, sometimes it's to the left, sometimes it's to the right. Where's its average position?
In the middle.
Right in the middle, even though it's never there. Isn't that weird? So what's the positive and the negative gonna do then? Cancel out, and you basically have, yeah, big deal. 2 zero charged objects. They're not gonna attract, they're not gonna repel. I could put them anywhere I want to, and they're just gonna sit there. Does that sound like a bond to you? What should a bond behave like? If I pull them apart and let them go,
They'll come back together.
they'll come back together. What if I shove them together
Come apart.
and let them go? They're going to want to return back to, what would you call that distance?
Bond. Bond.
Isn't that the bond length? Well, we're going to add a word to that because we know physics, bond length, it's going to be the equilibrium. An equilibrium bond length. Why am I calling it an equilibrium?
Sum of forces are 0.
That's right. When you're at an equilibrium, the sum of the forces is 0. But does that mean that they're always going to be 0 no matter where I put them? No, only at that equilibrium position. Does that make sense? We've talked about that in physics, right? So let's expand what we're talking about in terms of a graph. Watch this. I am going to make a graph of the forces. The forces repulsive. What about the attractive forces? The further away I get, they're going to look like that. Does anybody see anything symmetrical about these graphs? What do you think they're going to add up to? Right. Everywhere. They're going to add up to 0 everywhere. If I take this height and that depth, they add up to 0. That height, that depth, add up to 0. That height, that depth, they add up to 0. Does that sound like a bond to you? No matter where I put the atoms, they're always going to be 0?
Yeah.
Who said yeah? I'll slap your face. Strike that from the video. No, only kidding. I really want to slap them. If you put the atoms anywhere you want to, that's not a bond. How should the bond behave? If I move the atoms apart and let them go, there should be a net inward force, right? And if I push them together and let them go, an outward force. Well, it turns out that that model didn't work. When you talk about protons and electrons, and we talk about that orbital stuff, now the electrons don't quite do that. Who knows something about quantum mechanics? Are the electrons really going in an orbit?
No.
Remember that cloud model? Yes, very good. Wish I had that on video. There's a cloud, and can the orbits then be deformed? Could you get like a big cloud in the middle? What do you call it when the hydrogen bonds to a hydrogen and that bond is along the axis? What?
Single bond?
A single bond, and it's got a name. A sigma bond. Well, this is quantum mechanics. You've heard about this stuff in chemistry, haven't you? Okay, so let's make a graph of what happens when the motion of the electrons behave differently. Now, I can only tell you that it looks like this. Quantum mechanics is a strange thing. We have the repulsive forces that look like this. Now watch closely. And we have the attractive forces looking more like that. Does anybody see a asymmetry here? I'm going to push these up a little bit higher. Like that. Does anybody see an asymmetry? Because the electrons have now moved and they're behaving not in a clear orbit, we get an asymmetry. How do I add these forces? Yeah, just plus and minus. Take a look at this. Do we have more minus than we have plus?
Yeah.
So let's say that was plus 1 and that was minus 3. Where would I be? Minus what? Minus 2. So I'm going to put a little dot here. As I move inward, it looks like the attractions are dropping a little bit more than the repulsions are increasing. Now what about here? Look at that height and look at that. I'm here. Now look at this height and look at that height. I'm here. What happened right there?
Zero.
What's 0?
Equilibrium.
Yeah, I've reached an equilibrium position. Now what's going to happen here? Look how high that is and look how small that is compared to this. Where do I put the green dot? Above. And then this is continuing on, so it's up here. So now my question to you is, will the forces add up to 0 everywhere like in this diagram? No. The forces add up to 0 only in one place. What do we call that place from physics? That's the equilibrium position. So this length right in here, that is your equilibrium bond, hello, length. That's the equilibrium bond length. What happens if the molecules are closer together, the atoms are closer together? We're up here, aren't we? And then what will they do? Repel, push apart. What happens if they're further apart? They're out here. They're in the attraction part, and they're going to come back. So the atoms tend to oscillate back and forth about the equilibrium bond length. They're going to, or an equilibrium position. Well, I have a quick little demo here. I think I showed this to you once. I got a lot of demos. Did I show you this with the magnets? No. You're going to watch my magnets? What are you doing? You're watching the board? My goodness. The action's right here. Here's my magnet. Here comes another magnet.
Magic.
Yes, it's magic. Does anybody see what I just did? What's pulling the magnet down? Gravity. What's holding the magnet up? The repulsive force of the magnet, right? Where does the magnet settle down? At the equilibrium position. This is my model for two atoms forming a bond. You get that? Now, what's going to happen if I have another atom in there? Okay, let's see if I can do this. Big pressure because I'm on video. Oh, what do I got? I got a bond and another bond. You get that? Let's disturb this one. Whoa, I disturbed it. Hold it. It's making that one move. Isn't that cool? Now, I'll let you play with this someday. I got more of them, and you can see if you can get a third one and a fourth one. Isn't that neat? So this is my idea for the structure of matter. Did we have an experiment where we were pulling on rubber bands? So if we pull on them, they want to pull back, right? And of course, if we could squish the rubber, it would want to return back to an equilibrium bond length. Does that make sense? So what we're doing here is looking at a model on a microscopic scale and saying, hey, maybe that's what's going on the macroscopic scale, and we go back and forth. You with me on this? Okay, let's go back to the board now. Okay, so I'm gonna graph this over again up here. That's the, I wrote classical physics. You should write on this one, quantum mechanical model. Hello? Okay. Now, I'm going to draw this again up here.
So the quantum model is like in real life?
Yeah, the Bohr model doesn't work if you're trying to form bonds. Those circles, you'll just get a force of 0 everywhere. So now what about this? Here's a force. Here's the radius. And what do I mean by radius? Here's a hydrogen atom. Here's a hydrogen atom. This is that R I'm talking about.
And the distance between the protons?
Yep. So here we go. Watch this. There we have our force graph. That's not based on classical physics. That's based on the quantum model, right? You've seen this before?
Yeah.
Well, I'm glad to hear you say that because I think now that you know a little physics, maybe things start to make a little more sense. Okay, now wait. The graph gets better. That may not be the exact graph you saw. What I'm going to do now is I want to graph the potential energy versus the distance. Now get this. I have two atoms really far apart. That when I'm really far apart, the potential energy is going to be 0. Here comes the atoms. They're coming in together towards each other. I'll leave that one there. Here comes the atoms. They're coming in. That force is attractive and it's going to want to pull them in. What will they lose and what will they gain? Say it. Right. They're going to lose potential energy and gain kinetic energy. Does that make sense? How can I see what the potential energy is here? What force, distance, what on that graph represents that loss of potential energy? No. I'm looking for a key word that we've talked about. No. Somebody said it. What? Area. Why area?